Hello, everyone. This is Elisa Baum. I'm GridGain Systems Senior Director of Product Marketing. I'd like to thank you for attending today's webinar. It's part 2 in our series, In-Memory Computing Best Practices. The title of today's presentation is Adding Speed and Scale to Existing Applications, and it's being presented by Rob Meyer, who is GridGain Systems Vice President of Outbound Product Management. With that said, I'll turn the floor over to Rob. Go ahead, Rob.
All right, folks. So hopefully everyone can hear me. If you can't, please just raise your hand and we will try to take care of you. So welcome to the second session of the In-Memory Computing Best Practices. This is meant to be focused on helping understand the people, the processes, and the technology you as an IT organization need to put in place to be successful. That's what we're going to be talking about here. What we started with the last session, which was the introduction to the whole series, and what we'll be talking about in the whole next set of sessions to come. We are going to start, or we did start, with building a foundation for in-memory computing, which is a foundation for digital business and a foundation for improving the customer experience. We're now jumping into the second session. So if you remember the first one just a little bit, we talked about how to build that foundation, how to focus on building everything based around the customer experience, how to design for that experience, how to build a new real-time layer, design for speed and scale, and how to start building your roadmap, thinking about how to choose your projects and in which order. This session is all about the first project that most people see in their journey first, which is adding speed and scale to an existing application. Now, one of the biggest challenges we usually see here is people accelerating the wrong architecture with hardware. I had an architect friend who I worked with on low latency messaging. And he once referred to high-end appliances for real-time data warehousing and for messaging as an example of using hardware to accelerate the wrong architecture. And the same is true here with trying to accelerate existing applications. The challenge that most people, most organizations go through is trying to handle the load of new projects like APIs, like digital business, putting a load on their existing apps. And this is usually the first project where people apply in-memory computing. Why is that? It's because the existing applications are falling down because of all that new load that's been added by some of these new initiatives, like mobile apps as they relate to digital business. Most companies figure out how to open up their apps and layer web or mobile apps to create more customer self-service or to create new services, new offerings. But under the covers, the existing apps hold most of the business logic and the data, so it makes sense to use them under the covers. They're usually existing teams focused on these apps, and these existing teams have existing budgets, or they have the ability to ask for new budgets. Those apps going down is not an option. It literally takes down the business. So often they feel that they have to throw hardware and more software licenses at the problem. But here's the first challenge. These apps generally were not designed to handle this type of scale or deliver this kind of speed. Regarding the scale, we talked about that a little bit in the last session. But we basically experienced somewhere between 10 to 100 times more queries and transactions over the last decade. I get slightly different numbers depending on who I talk to as a customer, but the analysts will tell you roughly the same thing. The load has increased 10 to 100-fold over the last decade as we've gone more digital. We do a lot more research to buy things more frequently. Just think about how we shop on Amazon. We do 10 times more searches there. We do 10 times more searches looking for airline tickets or hotel rooms. And we do a lot more smaller purchases more frequently compared to when we used to drive to the store each week and pick everything up all at once. So we see 10 to 100 times more load. We're using a lot more data. 80 to 90% of the data that's stored inside an organization today is what we still call big data: social data, machine data, sensor data, data about your interactions online, all of which is used to try and track, try and personalize each and every experience. So that's really the data growing, the scale that we're dealing with all this data. Then there's the speed that we become used to immediately gratifying experiences. We expect to get things done very quickly online versus the hours or days or weeks it used to take in traditional car buying or other types of experiences. And so think about everything you have to do to deliver that fast and easy experience. In particular, how do you handle 10 to 100 times the scale using 50 times the amount of data and deliver this all in real time? That's the challenge. Now, you can look at this as a point problem and look at each individual application as it's falling down and try to scale it up, because often scale up was the only type of approach, the type of scaling that you could do with these applications. The challenge is that it's not just about scaling up each individual app. You actually have to first merge all the data together across several apps before you deliver it to an API or a mobile application, because customers are just expecting a single view of all their data across these applications. They don't like silos. That's not what they're asking for. So first you have to merge the data, and scaling up doesn't merge it. Second, you have to lower the latency. People are expecting a real-time responsiveness whenever they're using their mobile app. That's what I expect when I'm using it. Jumping across the network to a new layer, which then has to go fetch the data from all these underlying systems that are already slowing down, just takes too long. Something needs to be there to lower the latency. And third, this is a very expensive way to go, and it's only a Band-Aid, because scale up is, if you're listening to this webinar, you probably are facing this issue. Scale up is very expensive. It is not a pleasant conversation to have with a CFO who did not budget in the extra hardware being thrown at the existing ERP, CRM, and other applications. And it's only a short-term fix, because the amount of growth here, the 10 to 100x growth, is actually faster than Moore's law. There is only so much speed and scale you can add to a single box, and it's not enough to keep up with the growth. So there's really only one way to do this. And we'll talk about that. But don't do one-off investments in hardware. What people are doing is they're taking that money, expensive scale-up hardware money, and instead of just using it as a Band-Aid, they're investing it in the right architecture up front. That right architecture, the way it works is, first, you add something that scales out, that can merge the data using lower cost scale-out infrastructure. Two, use memory to move the app, the data closer to the app and into RAM, so that you don't even have to wait for a seek to disk, a search to the disk, to get at the data. And that's how they're lowering latency. They're moving the data as close to the app and putting it into RAM, usually on the same box as the app. And then third, for speed and scale, you're going to have to co-locate the data that you're working with the app, with the API, as close to the customer as possible to achieve the speed and the scale you're looking for. Once you merge all this data, you quickly realize there's no way to achieve, to put all that data together on a single box. You have to scale out. When you scale out, you need to make sure you don't have to fetch that data over the network and wait for it, because it turns out, if you do the math, you can't move a lot of data over the network. It takes a second to move a gigabyte. And these applications, when they're at scale, are using a lot more data than that. So what you need to do is make sure the data is already there with the API, with the app, by the time the API or the app needs it. And that's what we call co-location. MapReduce in Hadoop was one of the first examples of this for scale as well as for speed. So the first best practice is this. In order to solve all these problems, you need to build out a horizontally scalable architecture that layers in between your existing data and your existing and new apps and APIs. That's what we call an in-memory data grid in technical terms. And we'll go through how that works in a little bit more detail. But if you go back to the example of ING and what they were trying to accomplish, what they talked about in the In-Memory Computing Summit, this is actually one of their slides, one of Levin's slides from when he was going through how everything fit together. On top of the existing apps, on top of their existing channels that they had, they built 2 layers of APIs, both of which were built on in-memory computing. The first were the data services that actually pulled the data, merged it together across different apps to create a customer API, for example, and then bring the data for each API into the API, literally in memory into the API. That's what the data services did. The second layer was more about the customer experience. That's actually the CE in ICEP, their business service layer. The state of what the customer is doing, their session, their other information that they're using is stored here. It's all in memory with the API. That's how they were able to achieve getting from where they were with 200 or 300 milliseconds just in the latency of all their middleware that was accessing their data, down below 100 milliseconds every time for a really good, consistent, responsive experience for their mobile banking. From there, it just kept going. They then have to layer, and this is typical API management, you layer your security and your identity management, often in a couple DMZs on top to protect the APIs and harden them. Then you might be using cloud infrastructure, SaaS, software as a service, with your existing business functions that you've now exposed as what are basically on-prem APIs. You might need to combine them with some cloud services. You might need to bring in some data from the outside world that's tracking the customer, that's giving you social information about the customer to help you make better decisions. On top of all that, then you're building the better omni-channel experience. Then you're assembling new processes, combining your on-prem, your cloud, making better decisions with all that data. This is everything it takes to go from where you are today with your existing channels and apps to where you need to be or where you want to be with an omni-channel experience. It is a lot of layering. It requires something with the speed and scale to get as close to that new omni-channel experience as possible. That's how most people use us. That's how folks like ING use GridGain. That's how thousands of people use Apache Ignite. They'll often start by layering in between an existing application and the database that's underneath it. And then from there, they'll start opening these things up as APIs, the data that's inside, that was locked inside those apps. They'll start storing some of that new information natively using the persistent store to store some of that social data and some of the other data they need. And then they'll start trying to make more intelligent decisions, processing the streams that are coming in, maybe using something like machine and deep learning, what we call the continuous learning framework, to automate some more intelligent decision making to make that omni-channel experience even better. The first stage is really the in-memory data grid. And I just want to make sure everybody understands how it works in a basic way. It typically is used by sliding it in between an existing database and app and making the app think that it's still talking to the database. What it does is it literally passes through all the writes to the database and coordinates with the database using transactions, which is something that's been proven for years, but completely offloads all the reads from the database. It becomes the new system of record for that application, which thinks it's just dealing with its old database. So here's what it needs to be able to accomplish this. First, when you slide it in between your existing app and database, it becomes a read-through, write-through cache. That's a read-through, write-through cache pattern that people are used to implementing if you've worked with caches, to let the app keep thinking it's talking to a database. Since most apps are built on SQL, it needs to support SQL and the other functions around SQL, including ACID transactions. For NoSQL databases, it also needs to support key value at the very least. So at the very least, you're looking for SQL and key value support in a memory data grid. From there, it connects to your existing database and pulls out the schema, the DDL from that database, recreates the tables inside the data grid all in memory. It then does a one-time load of the data from the database to get up to date, to get in sync with that database. And from then on out, handles all the transactions, the reads and the writes from the application. The way this works is you, as a developer, hand the application new ODBC or JDBC drivers. Okay, so now it knows to talk directly to GridGain or Apache Ignite, which is the open source foundation for GridGain. Now the application points to GridGain. For each write, GridGain receives it, it passes it through the database, and then on a successful commit, GridGain's transaction coordinator, which is a global XA coordinator, commits the change first to the database, and then on success, commits it to the cache to in-memory. If anything fails at any point, it all gets rolled back, just like you'd expect from a traditional transaction. Now that the data in memory is completely in sync with the database because it's been handling each write, GridGain can handle all the reads. Whenever a request, a query comes through, the query is executed directly on the data in memory and returned without impacting the database whatsoever. So it gives the existing database a lot more headroom for growth. Typically 60% of the load on a database, maybe more, might be reads. It certainly becomes more as digital business starts overloading the existing applications. So you've created a lot more headroom for growth for that existing app. And in the process, you've now moved to a scale out, horizontally scalable infrastructure for handling all the reads, which can be done on any kind of low-cost infrastructure. So this not only allows you to scale out now for the reads, which is causing most of the headache of the load on those applications, it actually gives you a way of opening up that data to other uses. Because while it supports SQL and it supports key value, that's actually usually implemented on top of a compute grid of some sort. It's a general purpose computing grid where you move computing to the data and execute the compute directly against the data and then roll up the results. The way MapReduce works with Hadoop, this is just a real-time version of it. So it allows you to execute faster on each node with smaller amounts of data and then roll up the results. That also tends to lower latency and improve responsiveness. So in this kind of architecture now, you can actually throw any kind of compute at the data. You can co-locate individual nodes of data in the grid directly with the web app or the mobile app infrastructure. You can also co-locate it with new APIs so that you can bring the data directly to the API and lower latency. That's typically how this kind of infrastructure works. Sometimes you also have service grids that are tailored for APIs and for deploying and managing APIs. GridGain happens to have that as well, so that you can more easily deploy APIs and their nodes together. More on that in other sessions as we talk more about APIs. So the first corollary here is don't accelerate the wrong architecture with hardware. Scaling vertically will not work in the long run. It doesn't scale enough. It doesn't lower latency. It doesn't support new data or emerging data. And it's not going to be the right answer for APIs or any kind of analytics for both speed and scale, because it doesn't merge all the data and it doesn't bring the data any closer to the API or the analytics where it needs to run. The only real approach is to go have a horizontally scalable in-memory architecture like an in-memory data grid that can move the data closer to the customer and deliver that kind of horizontal scale. The second corollary I wanted to bring up is, yes, it's about speed and scale, but it's not just about speed and scale. Stay focused on the customer experience. One easier way not to focus just on one app is to focus on why that app's getting overloaded in the first place. Have a sponsor who's driving this across the applications. That will make it easier organizationally to get the right things done. It'll help you look ahead and plan ahead to build the data layer that you need to build, improving that customer experience over time. And if you don't know the right architecture or the right people, just ask the right questions. That is, of course, why Socrates was poisoned, for asking the right questions. But ask the right questions. Do the math on how much scale you need in the longer term, not just for the first year or two, which a Band-Aid like scale-up hardware might solve, but the longer term. Ask who else is using the data that you have. Is it being used by an analytics team using some ETL? And what are their challenges with analytics? Do they need real-time analytics, and can they deliver it? They often can't. What analytics do you need to do for the new teams that are building the new APIs, trying to improve the experience? So what data do you need for what either of these two teams need? And you'll be able to chase down what other types of data outside that individual app you'll need to merge with the application data that you have. Okay. Back in part one, we talked about not violating the laws of physics, which was a great line by Chris Berry from HomeAway. He used it when he was talking about network bandwidth preventing real-time business because the data has simply become too big to move. But for me, it's a general statement. If you have systems that are either batch or by definition can't be real-time, you can't build a real-time business on top of them. You have to build a new real-time layer on top, and then you need to coordinate between the two. This is the next best practice. Choose the best integration architecture between the new real-time layer and the existing non-real-time apps. When you build that new layer, you're building a new real-time business, and as you do it, you need to think about how you keep this new layer in sync with your old layer, or your existing apps and your existing business in sync with this new business. There are two types of integration that you can choose. The first, let me describe it this way. Imagine trying to give a customer a real-time business. Like when you're paying your bill, in real time, you look at it as paying your bill, but it's actually built on a batch-based system that's settling the bill overnight. It isn't paid until sometime in the middle of the night or up to 24 hours later. And if you have a batch-based system, that is your challenge. Because you may, in the case of 24-hour fitness, for example, this was their challenge. People would pay the bill. They would then look to see if the balance was paid, and it wouldn't show that it was paid for up to 24 hours. So people kept paying the bill again and again and again. It wasn't only annoying to the customer, who really became dissatisfied. It was annoying to 24-hour fitness as well, because they then had to manually go and back out these extra transactions, apologize to the customer, and that ended up being very costly to them. So you have to figure out how to make a real-time business in front look real-time while still faking out the batch system and letting the batch system operate as is. In the case of 24-hour fitness, what they did was they actually would do a real-time update in the in-memory layer. They would update the account balance, which they had as a real-time record. And then they would just pass through the bill payment to the batch system. The batch system would then update. Once it ran, it would update the real-time version and say, okay, payment taken. This is actually option A in one of two approaches you can take, which I call Synch or CDC. So here's the challenge. When you have multiple apps that are writing to the same data, and some of them will be in a memory data grid and some of them won't, you have to figure out how you're synchronizing between the old and the new. And you really have two choices. The first is what 24-Hour Fitness did. You slide a read-write grid in between each application that you're scaling and the database. For the applications that don't write through the in-memory data grid, you have a synchronization layer that watches for specifically for those changes and updates the in-memory data grid. In this case, when the payment was settled in the backend system without the apps above the in-memory data grid knowing, the synchronization layer updated a field in the in-memory data grid that said payment processed. That's one way of doing it. The second way of doing it is to use change data capture, or what some people call CDC. It's been called CDC for a good decade. In this case, this is one of the reasons, by the way, that we added a Golden Gate connector, because Golden Gate, one of the bigger change data capture solutions on the market, was being requested by several of our customers to do this kind of integration pattern. So the way CDC works, it puts a really low load on the database, typically between 2 and 5%, and looks at the write-ahead logs that are used in transactions. It doesn't directly go into the database. It uses the write-ahead logs to capture each and every write exactly once. It typically streams these changes out. So it's a change data capture. So in this case, what you do for all the writes is you let them be. You let it write directly against the database. For all the reads, you are streaming them off via CDC directly into GridGain, so that for all the reads, the applications can directly hit the in-memory data grid and offload all reads from the database. So you trade off the 60 to 80% load for 2 to 5% load of CDC. The downside here is there's a little bit of latency between when you write something and when it shows up as a read in the in-memory data grid. So here's the trade-off. If for you need you have control over all the apps you need to change, and you need immediate consistency, meaning you cannot have a delay between when you write and when it shows up consistent in your read layer. And you're not really concerned about write collisions across applications, that there won't be. There's no real concern between the new apps you're upgrading and the existing apps that are writing directly to the database or doing batch. In this case, implementing a full in-memory data grid read-write pattern between each of your new apps and having this integration sync layer, this works. The benefits are it's immediately consistent, and once you've actually layered an in-memory data grid between all of your apps and that underlying database, the sync layer isn't needed anymore. You can simply flip it off and you've completely done with your transition. You've now built a layer that is 100% between all your apps and your database. You could actually replace that database. You could be writing to a new store. You're completely insulated from your underlying scale-up only data infrastructure. So you have a lot more flexibility. The synchronization layer can get a little tricky. We're used to that, but it can get tricky. It can take some work. On the flip side, change data capture or CDC is useful when you don't have control of all the apps. When the apps do share a lot of data, and there could be a lot of collisions across them, and you're not that worried about immediate consistency. It could be a second later, or there aren't going to be those kinds of collisions. In this case, CDC becomes a really clean way to populate a cache, which is basically an operational data store, a pattern we're used to for probably 20 years now. This approach has been done. It's proven. The work is in redirecting all the reads in the existing apps and pointing those existing apps to read from the in-memory data grid, separating them from the writes. The benefit here is if you do not have control over changing all the apps, you can't just do that for organizational reasons or other reasons. It works. And the integration layer is easier. It's just change it to capture, streaming everything, all the changes into GridGain or some other in-memory data grid. Now, some of the challenges here, you can't just turn off your database at the end. And if you need to move the writes, then you need to do it for all the apps at the end. It's kind of like you're kicking the bucket to making all your changes across all your apps at the same time. That may not be an issue. You may never need to change your writes. It's possible, but that is an issue if you are continuing to scale your writes and not just your reads. But here's the short-term answer. Both work. Synch or CDC could be the better answer for you depending on where you are. So you need to consider both and you'll need to choose. So this is the best practice. Choose Synch when you need control, you need immediate consistency, or you need these for other projects. Look ahead and see, do I need immediate consistency? Do I need to scale my writes? Otherwise, you might choose CDC, and that's fine. The third best practice I like to refer to is free your data now. And for those of you who are in love with the matrix, it really is a choice of, do you take the red pill now and free up your data to allow it to be used by new APIs or analytics? Or do you take the blue pill and wait until you need to take the red pill later? In this case, it's actually okay to take the blue pill for a while. It may be more cost effective. You just need to decide when is the right time to take that red pill. So here's some guidelines for trying to figure that out. If you need existing data for new APIs, if you need to perform analytics and use that existing data that's in there, so you need the real-time visibility into that data, then free that data now. Move it into an in-memory data grid using a read-write pattern. Once it's in the in-memory data grid, it can be used by other apps just by scaling out horizontally. We're not going to impact the performance of that existing app because these scale-out architectures just work that way. And then it can be used by other apps. All the reads will hit the in-memory data grid. All the writes will be directed to the database that now has more room because you offloaded all the reads. And in a read-write in-memory data grid pattern, you could actually persist the data somewhere else if needed. So it does give you a way out of some of the write scale-up limitations of that database too. So look ahead. If that project is needed down the road within the next year, it might actually make sense to move it now, take the hit, and design to support that future project. Might also make sense to move related data into an in-memory data grid to simplify integration. The sync layer that we talked about might be more complicated than moving just one more app into the in-memory data grid and having a clean in-memory data layer for everything. If I was in that situation where I could avoid building the integration layer, I'd do it in a heartbeat. It's just cleaner and it's actually lower risk for all the other applications involved. The next best practice is really about redesigning for speed and scale. It's good to understand when you go to an in-memory data grid and you start scaling horizontally that you might actually need to start redesigning some inherent things in your application. As architects, we like to take smaller hits over time than take a major hit all at once. And that's exactly what this is about. So when you move to an in-memory data grid and you scale your data out, you have to think about how your data gets partitioned so that you can move related data that would be used in a join, for example, to a single node so that you don't have to fetch data over the network as you do your operations. For example, if you're doing a join across two tables, you would make sure that the data that's related across those two tables by a foreign key is on the same node. So you want to partition your data as you're writing it in, as you're distributing it, to make sure they're co-located on each node. That's the type of thinking you have to do. So you might want to do a filter before a join when you're doing distributed SQL. You might also need to change your SQL in the order to get that done. You might even need to change your database schema to make sure as much of the processing can be done on each node as possible without moving the data. You might not need to do that right away. You might have a lot of headroom for growth before you hit the wall and you start moving too much data over the network. But you need to plan ahead, because eventually you probably will need to do these kinds of redesigns. And when you're using an in-memory data grid, the way you do it is you redesign the database. You then move the schema back up into the in-memory data grid so they're identical. And at the same time, you need to make sure some of the SQL in your app has changed. Now, you do have one other option here. Instead of doing a synchronous in-memory data grid pattern, you could do an asynchronous one. You could build a completely new 2B schema in your in-memory data grid, and then asynchronously push all writes to the database that has a different schema. If you're the only one writing that data, you can do that. I'm going to leave this for a more advanced topic, and come to us and we can explain it. Maybe we'll do it in a future webinar, but I will say this. Large distributed systems work better when you don't have to do everything synchronously at scale. The other thing I want to point out is you're going to need to remove PL SQL over time, but you should do it. I know it's painful. It's like getting wisdom teeth pulled, but it's necessary. You use PL SQL because scaling up made sense. Embedding those stored procedures made sense to get it closer to the data, to run it faster. But you're scaling, and the way you're adding speed and scale is no longer in the database. It's scaling out horizontally and moving everything into memory outside the database and co-locating processing with the data outside the database. So as you look at new APIs, as you look at new analytics, you're going to have to figure out how to pull that stuff out and move it into the new data grid. You should think of it another way, that an API, as you build new APIs, you're going to restructure your data. You're actually looking for ways to decouple the data from the business logic. So when you design your data models, you need to think about what logic needs to be co-located for an API and design for it. The logic still is logically separate. You write it in SQL, in Java, or .NET, or some other language. You should be able to run it on the compute grid. So look ahead for those other projects and think about how the data will fit into your new model. Meaning, if you have to add data from another app later down the road, at least make sure in your current data model that you're building in the in-memory data grid today, that with indexes and maybe doing caches of the data in a separate cache, that you can successfully merge that data together. You don't have to redesign necessarily. You just need to make sure your data model is extensible enough using indexes and other means to support those future projects. Next, design with APIs in mind. You're designing for speed and scale. You're looking ahead, and there are really two big workloads you have to watch out for. The first one are APIs. We'll talk about the second one in a second. But APIs are critical. They're really just about everything you're doing with digital business has an API. For your mobile apps, for your Internet of Things, for integrating with SaaS applications, all of that is about APIs. If you talk to Gartner, I'm sure many of you do, Any type of cloud native app development you're doing will probably use in-memory computing. You'll co-locate the data with the APIs for elastic scaling. The majority of our customers do this. Docker is used by the majority of Ignite, of all Ignite users. So thousands of companies, the majority of them are using Docker on-prem or in a cloud. By, within the next 3 years, certainly, you'll see your companies adopting in-memory computing platforms and consolidating that effort. And if you think about it this way, maybe it becomes simpler to think about it. If you don't consolidate your in-memory computing, which holds another copy of your data somewhere, you're ending up with many more copies of your data and more versions of the truth, similar to what you had to deal with application and data integration in the past. That you somehow down the road have to integrate back together to maintain a single real-time view of your business. You do not want another integration nightmare like that, whether it's on-premise or in the cloud, let alone the additional complexity of keeping all these different technologies, these pieces and parts up and running together. You want to take control of that now and make sure you're keeping your data in a single place. And the same is true for in-memory databases, by the way. The more data that comes into the organization, rather than storing it in many different places, we're seeing a continued push to try to consolidate a few pieces of data. So here's the next best practice. Design with those APIs in mind. Most of the new projects we're talking about use APIs, whether it's B2B integration, digesting social data, building mobile apps, integrating with SaaS. In-memory data grids are ideal for APIs. You can merge the data that's needed for the API really reasonably well. It doesn't take a lot of effort. You can deliver the speed and scale they're asking for. You look like JSON or SQL, it's your choice, because in-memory data grids should generally support key value and SQL. They're Docker and Kubernetes friendly by default. They work really well in private cloud infrastructure like OpenShift or Docker Enterprise, or the list goes on. Because they're API native, relatively new technology, in-memory data grids can easily use APIs and easily be consumed by the API security infrastructure for locking those APIs down. So make sure to support API security, make sure to co-locate your code with the data and design it to be co-located for speed and for scale for other use cases like HTAP. Now, when is the best time to have data about the customer? The answer, of course, is now. When you're talking to someone, when they have a problem and want it solved, it's now. This is what HTAP, or hybrid transactional analytical processing, is all about. It's all about bringing real-time smarts and automation. The challenge is that adding the smarts to digital business is hard. We're used to having two pipelines, one for online transaction processing and a second one for analytical processing, or OLAP. We did this originally because we allowed apps to be broken up, and we didn't want to overload each individual analytic or each individual app with the analytics as well. So we have this extract, transform, load process for grabbing data changes and then merging them back together with historical data to give ourselves a historical picture of the business. But OLAP is not real time. It can't be, because ETL is outdated the second it starts. It's creating copies of the data and doing all kinds of things to merge the data from all these different sources back together. Existing OLAP can't handle the additional loads. It's partly why they're separate. And it doesn't have hooks to easily add OLAP. And the data just got a lot bigger than the network can actually handle. That's where HTAP comes into play. That's why you need to design with HTAP in mind, because you need to design so that you can improve the customer experience or improve some aspect of business operations, you can easily add the analytics on top of the data that you have during an operation or during a transaction and pull it together in memory and at scale to be able to do this kind of real-time analytics while you're interacting with the customer when you're doing something now. That's what HTAP means, and that's why in-memory computing is the foundation for real-time HTAP, for in-process HTAP, because it's the only way to run these analytics fast enough. Meaning it's the only way to do this is to make sure that the data is already together, already in memory, already in the same place as where the transaction is taking place. That's what an in-memory data grid does really well, especially if it also has a compute grid for running any of the logic and co-locating the logic with the data. Gartner calls this approach hybrid transactional analytical processing, or HTAP. 451 calls it HOPE, or hybrid operational analytical processing. I like HOPE in part because I do like HOPE. But you need to execute analytics during any interaction, not just the transaction, to improve the experience. And that's one of the reasons I like that term. But this is your new architecture. So what it means is that you have to design with this new kind of approach in mind. You need to think about what data you need in a memory data grid for analytics, not just supporting that existing app. And make sure either you get it there now or you can support it by adding the data later and merging the data together. This means looking ahead yet again. And there are two ways to identify the right data and the right analytics. You can look at your existing analytics, that whole ETL pipeline, and see what needs to be real time. You can take some of the projects where they're struggling to make it real time and consolidate that into your project now or later. You can look also at the new APIs and the new projects and plan ahead with them to figure out what kinds of analytics they'll need to improve some kind of experience. And that's really how you identify the other data. So hopefully you have a sense now about some of the more common best practices for adding speed and scale into your infrastructure to add it to existing applications. Use the money from the scale-up hardware that you're going to spend to invest in the right architecture. Build out that horizontally scalable in-memory data grid to add speed and scale. Choose the right integration architecture as you're doing this to transition from the old to the new, whether it's Synch or CDC. Decide when you're going to free your data, how you're going to, and when you're going to start adding the speed and scale, making those incremental changes in your data design over time. And design with your two newest, most common workloads in mind. Design with APIs and design with HTAP in mind. So that's all about adding speed and scale. Next up in the series, we're going to talk about how to develop for new apps, for new APIs, and go through some of the detailed best practices there. So we'll dig deeper into what it really means to build and support new APIs within memory computing. So with that, let's move to one or two questions. I see there are one or two. So let me read. We have time for just a couple. The first one is, how does this differ from something like a Redis or a cache aside pattern? I'm paraphrasing here. Typically, if you look at how some caches like Redis work, you will go in and you will start changing your application. You'll write code to take data that you've just fetched from a database or data that you're writing, and you're going to do a second piece of code to write that data into a cache or pull that data out of the cache. And you'll write additional logic to manage whether that data in that cache aside cache is up to date or not. In some ways, the CDC pattern is a little bit like a cache aside. It's a read-only cache, but it's automatically being updated by the CDC from the database. So it's actually almost in between a read-write in-memory data grid and a cache. But it's not quite there. The problem with a read-write cache is, A, you need to change your app extensively because these cache-to-side caches do not support SQL. So you're writing in another language and ripping out some SQL. And B, you have to manage whether that data is up to date or not. You have to decide when to invalidate the cache because it's not automatically in sync. So you have to do the work and add that work into your application. And that's one of the biggest challenges. Okay, well, I'm getting the signal we're a little bit out of time here. So if you have any other questions, feel free to email. You can always just reach me at robmeyer@gridgain.com and submit your questions, and we'll try to get them answered. If you're looking for more resources, feel free to visit us on gridgain.com or find some webinars on the inmemorykcomputingsummit.org site. Plenty of great resources there as well. We have a bunch of white papers that go through some of these topics, some videos, and feel free to just download and get started, whether it's here or on GridGain Cloud, which is cloud.gridgain.com. So I want to thank everybody for attending, and I guess we'll cover the next part in the series in the new year. So in the meantime, Happy New Year to all.